Hi, welcome to the new series on inner product spaces. Okay, uh, see, in the first part of linear algebra, you talk about vector spaces over any field. Even though I confine myself to the field of real numbers, it could be the field of complex numbers or rational numbers or finite fields like Z mod P, etc. Or any field for that matter. If you know that word, it's fine, otherwise ignore. Okay, so there was no additional structure in the sense that I can't talk of length of a vector in arbitrary vector space as of now, right? But those who have seen R2, R3 and physics, you might have seen, you talk about length of a vector, direction of a vector, angle between vectors, etc. So these are known as metric notions. So the linear algebra which you learned is essentially so far is algebraic. Okay. Now what we want to do is we want to introduce a metric concept. What do I mean by metric concept? Metric simply means I can measure something. Okay, what are the things I can measure? The length of a vector, the distance between vectors, and the angle between vectors, etc. This is what we want to do. Okay, and many students, when they look at the abstract definition of inner product, they are always puzzled why I want to do it. After that, it becomes pure again as usual algebra. The main reason for that is typically algebra books confine themselves to inner product spaces over complex vector spaces. Okay, but if you want to really understand the geometry, it's better to stick to, at least not to stick to, start with inner product spaces over a real field. There you can actually use, okay, all these things, the geometry can be brought out. And not only that, those of you who are very curious, you might have seen the so-called Euclid geometry is built out of axioms, right? Using axioms. But our inner product spaces, okay, two-dimensional inner product space or real field will give what you call a model for the geometry. Please ignore all these things. Okay, if I'm trying to intimidate you, you find that I'm intimidating you. No. Okay, but what the point I want to say is why it's important to start with the inner product space over real field. Okay, algebra teachers usually just want to stick to complex fields, or because of complex vectors, complex field is algebraically closed or whatever it is. Okay, right. So let us start with the thing. Okay, the second thing is, in the first part of linear algebra, we always dealt with linearity in the sense that, okay, something like ax plus by plus cz, or a1x1 plus a2x2 plus anxn, and so on and so forth. Almost, if you think of a vector space, let us stick to Rn, for example, write x equal to x1, x2, xn. So any object we deal with is first degree polynomial in the variables x1, x2, xn, the coordinates, right? But in the second part, that's a part inner products and so on, more general, what we are going to deal with is we are going to give an additional structure on the vector space, which involves second degree, okay, quadratic expressions in x1, x2, xn. Okay, these are all vague, but keep that in mind so that you will know we are essentially going to this higher level. It's not just abstract vector spaces, but vector spaces with some additional structure. What is additional structure? That's what I said by saying metric. That is, you can do certain measurements, because in modern, okay, world is full of measurements. Okay, you have to measure something or other, and linear algebra is the most important tool in 21st century mathematics. In fact, so much so that somebody says it's more important than even calculus. Okay, so you have to learn these things, and I will go very slow and bring out the geometry. These things are usually not found in standard courses and books, but you can find it in my book. Okay, we'll come to that. So the title of the lecture is Inner Product Spaces, session 1, and you have my email ID. And the only reference you will need for this course is my book on linear algebra, a geometric approach, because many of the things where I try to bring out the geometry will not be found in any book, to the best of my knowledge, or if you think you can, it may be scattered at many places. Okay, and you have my YouTube channel, and the most important thing, as you know, last several lectures I started saying you can download the list of videos which are available on my channel. This list is a PDF file. It has a description what is each video about, and it gives a URL and possible good references also which are mentioned in the videos. Okay, right, now let's get started. So as I said, we have thing. So what is that we want? What we want is I have a vector space V. Okay, hereafter our vector space will be only over R. Okay, vector space over R. Suppose V is a vector space over real. That is a real vector space. Okay, so what we want to talk about is we want to find or equip a new structure, a metric. Metric simply means you can measure. Metric structure on V, so that one, I can talk of length of a vector V in V, and two, I can talk of the angle between two non-zero vectors V and W in V. This is what we want to do, right? So I want to think. So far we learn only one aspect, only purely algebra. Now I want to put extra structure so that I can measure things. What are the things I can measure? I can think of the the length of a vector, and second thing is I can talk about the angle between two vectors. Okay, as you might have seen in your R2 or R3 or in your physics classes, you might have learned. Okay, a vector is a directed line segment, so it has a length, it also have a direction, and given two vectors you talk about the angle between them. All those things you have learned, so they are very much needed for any kind of real life applications of linear algebra. Okay, so that's what we want to talk about. Okay, now let's look at slow. I will go slow, I'll motivate all those things. Let us look at R2 in the coordinate geometry. Okay, if I have given a vector V equal to x comma y, okay, in R2 you learn the length of V. Okay, this is, I will denote by this is read as norm of the vector V. How did we define that? Let us quickly go through it. So I have this vector. Okay, this is my V. Okay, then what I do, you look at this, the coordinates are x and y, therefore this is x and this side is x. Maybe I will use a different color. This side is x, and whereas this side is minus y, which is mod b, right? Therefore by Pythagoras theorem, what implies the length of the hypotenuse is x squared plus y squared. This is minus y squared, but it is same as this. This is the unique non-negative square root of the vector v. Sorry, square root of the real non-negative real number x squared plus y squared. Right? Using this, we also define the notion of distance. Distance between two vectors v equal to x1 y1 and w equal to x2 y2. Then you define distance between v and w to be x1 minus x2 whole squared plus y1 minus y2 whole squared. This is again defined by Pythagoras theorem, as you have learned in coordinate geometry. I don't want to stop that because otherwise we will be stuck in 11th standard. Okay, junior college. Now we want to go to higher studies, right? Okay, is it clear? Okay, so right now in R3 I can do the same thing. Suppose I have a vector v which is x, y, z. Okay, I can't draw a good picture, but you must have seen in coordinate geometry. This is my V, right? Then what do? The length of V is, look at the project V orthogonally onto each of the thing. So you project this, and this is the vector you get. This is the projection on the xy plane. This is xy plane. Okay, project it, and this is the height. Okay, that is Z, right? This is a Z. This will be your Z, mod Z if you want, if because Z may be negative, even though I seem to have drawn the first arctan, but it may not be the case. Therefore length is going to be x squared plus y squared plus z squared to the power half. Again the unique non-negative square root. So since we have done it in R2 and R3, now we define, okay, there is no geometric justification now. If a vector V is given x1, x2, xn and Rn, we define length of the vector V to be square root of x1 squared plus xn squared, the unique non-negative square root. This is the definition now. Earlier the formula for V in R2 and R3 was justified by Pythagoras theorem. Is that okay? Very good. Next thing is I want to talk about angle between two vectors. Let us say V, okay, x1 y1 and W x2 y2 in R2, sorry, right? Now the way I want to do, okay, is very interesting. See, let us look at R2 and C. There is a bijection, namely if you give me 2 ordered pair xy, then I can think of the complex number x times iy. And on the other hand, if you give me complex number x plus iy, I can write this is the bijection. Again, as a vector space, this map is a linear isomorphism, right? So what I want to do is, let me write the vector x plus iy for xy. This is a complex number, and uv or say x1 y1 and x2 y2, that goes to x2 plus I y2. Call this as complex number z1, complex number z2. These are in C now, right? Now therefore what I want to know is the angle between two complex numbers. Notice that I am assuming these are non-zero. Okay, non-zero vectors, that is okay, right? Now I am going to use what you know about polar form of a complex number. I could have done it polar coordinates of R2 as you have done in your coordinate geometry, but it will be nice for you because we also want to talk about inner product spaces over C. So slowly I am preparing you for complex vector space also. Complex number. If you give me a z which is non-zero, you can see z is not equal to 0, right? X equal to x plus iy, then I can write it also as r e power I theta, where r is x squared plus y squared to the power half. Notice that this is nothing other than the vector normal length of the vector xy. This is not R2. The vector xy is not R2. The length is of course a real number. Alright? Do all of you understand this? So the way I do this is, okay, if this is my z, then this is my theta, and this is the length r. Okay, therefore this point is r cos theta in polar coordinates, r sin theta. R in complex numbers, r e power I theta. Do all of you agree? So it has a lot of representation, xy in xy coordinate, in polar coordinates r cos theta, r sin theta, and complex numbers polar form r e power I theta. Right? Okay. Therefore, what I want to know what is the angle between two things. Okay, z1 and z2. Therefore, z1 I can write as r1 e power I theta 1, z2 as r2 e power I theta 2. Right? Now, the angle between theta 1, z1 and z2 is either plus or minus theta 1 minus theta 2. Do you agree with that? It depends which way you want to measure. This may be z1 and this may be z2. Either I can go from here to here. This is theta 2, this is theta 1, right? My picture was not good, so let me again draw. Okay, this is theta 2, this is theta 1, right? Okay, right. So the angle between either theta 2 minus theta 1 or theta 1 minus theta 2. Okay, it depends upon from which way you go. Fine. Now how do I get it? The interesting thing is I can get it the following way. Suppose I take z bar w. What is z bar? Remember, z is r e power I theta, therefore z bar will be r e power minus I theta, therefore r e power minus I theta 1. Sorry, this is my z1, right? Z1 and sorry, z1 bar z2, r1 e power I theta minus I theta 1 into r2 e power I theta 2, that is r1 r2 e power minus I theta 2 minus theta 1. Is that okay? Okay, pause, review, proceed. Right, now let's do that. Okay, now remember e power I theta by de Moivre's formula is cos theta plus I sin theta. This is de Moivre's formula. Or maybe Euler's formula. I'm sorry, it may be Euler's formula. Okay, right. Now, therefore, look at this side r1 r2 e power I theta 2 minus theta 1. Okay, this the real part of this is modulus of z1. Remember, it's modulus of z1 is same as modulus of z1 bar also into this is cos of theta 2 minus theta 1, right? Therefore, what do I know? So I am taking real part of both sides. Z1 bar Z2 equal to real part of R1 R2 e power I theta 2 minus theta 1. This is mod Z1 mod Z2 into cos theta 2 minus theta 1. But let us do what is Z1 bar into Z2. Z1 bar is x1 plus x1 minus Iy1 and this is x2 plus Iy2, that is x1 x2 minus Iy1 into plus Iy2, that is minus plus plus, therefore y1 y2, okay, plus I times whatever x1 y2 minus x2 y1, right? Therefore real part of z1 bar z2 is x1 x2 plus y1 y2, right? Therefore what do I get? x1 x2 plus y1 y2 equal to, okay, the length of the vector x1 y1 into length of the vector x2 y2, because this is mod z1, this is mod z2, into cos of phi minus theta. Therefore I got the angle. So the angle between the two vectors, non-zero vectors of course, x1 y1 and x2 y2 in R2 is given by cos of phi minus theta equal to x1 x2 plus y1 y2 by norm of the vector x1 y1 into norm of the vector x2 y2, right? And do you understand this? Okay, pause, review, proceed. Now notice that if I have two vectors of various things, the length between them is same as the length between their unit vectors. Okay, unit length. Because remember, length of the vector is defined. Okay, length is unit for each of them. Right? You understand? Therefore, if Z1 is a unit vector, okay, unit modulus, which is same as saying the length of the vector x1, y1 equal to 1, which is equal to length of the vector x2, y2. The formula reads as x1, x2 plus y1, y2. That is equal to cos of theta 2 or phi minus theta 2 minus theta 1 or phi minus, I don't remember which one I wrote. I'm sorry, but is that okay? Did you follow that? Right? So this, okay, pause, review, proceed. So what I have found, if you are given two vectors x1, y1 and x2, y2, okay, the angle between them is given by x1, x2 plus y1, y2 by the length of these vectors. Is that clear? And if they are of unit length, then it is only x1, x2 plus y1, y2. So by looking at the product of the coordinates and summing them, we get an expression for the angle. That is the important thing. Not only that, notice that the length of the vector x1, y1 is also given by the same thing, right? x1 into x1 plus y1 into y1, right? Are you following? Okay. Y1 square. So this is the way I want to stop at something. Let us go to algebra. This is a trick which you should learn. You will see this trick I am going to use throughout the course in inner product spaces, right? Suppose on R, okay, suppose I get given, okay, two things. For any two real numbers x and y, I know what is x plus y. For any real number x, I know what is x squared. Okay, that is multiplication. Okay, I want now what is xy in terms of these objects. Okay, this is pure algebra, just high school algebra. Do not get psyched. Okay, what do I know? In R, suppose, okay, I know there is a multiplication, but I do not know how to multiply. But I know two things. What are the two things I know? If you give me an x and y, I know how to add them. And if you give me any real number, I know what is its square. Now, can I find what is the product xy? How do I multiply x and y? Do you understand? That is very easy, because remember, what is x plus y whole squared? Since I know x and I know how to add, and x plus y is a real number, therefore I know what is its square. Okay, remember, multiplication already given, except I do not know how to multiply. And similarly, x minus y whole squared also it's known. That is x squared plus y squared minus 2xy. Right? Therefore, I know subtracting one from the other, what do I get? 4xy, okay, equal to this fellow. When I subtract, what do I get? 4xy equal to x plus y whole squared minus x minus y whole squared. Therefore, xy is 1 by 4. This is 7th, 8th standard algebra. What do you think I achieved? Again, go back. Please understand, this is how you should understand concepts. In R, I know there is a addition and multiplication, but I may not know how to multiply two real numbers. But I know it satisfies all the properties, and this kind of formulas are also true. So if I, then how do I find x times y? You use the formula, right? Notice that I got everything. So what I am trying to say is, go back. So if I given a vector in R2, I know what is norm of xy. That is x squared plus y squared. That means norm squared is x plus y squared. Right? Therefore, what do I know? x1, y1 is in some sense x2, y2. How do I talk a product? There is no product. Okay? How to talk of some kind of, that is called dot product. This is x1, x2 plus y1, y2. Okay? Please, this may be vague, but as I keep saying, understand this thing. If you understand 30-40%, that's more than enough. Okay, as you go along, you will become more and more confident what I was trying to say, and you will also understand better. At present, do not try to break your head to understand 100%. Don't do that. Right? So what I said is, okay, I know how to define the norm. From that, I can try to define this. And if you notice, that is what we got here. Look at this. Given two vectors x1, y1, x2, y2, I got x1, x2 plus y1, y2. And norm of x1, y1 whole squared is, okay, that is same as saying take x2, y2 also as x1, y1. Then that becomes x1 squared plus y1 squared. Okay, do you see some kind of intuitively they are related? That's good enough. Okay, now let's go. So on Rn, therefore I am going given two vectors x equal to x1, x2, xn, y equal to y1 to yn. Okay, based on my motivation, I am going to define the dot product. Okay, of two vectors x dot y. This is by definition x1 y1 plus x2 y2 plus xn yn. And what is x dot x? That is x1 squared plus xn squared. And what did we know by x dot x? This we know is the length of the vector x squared. You follow that? This is what I was trying to allude. Why did I define the dot product? This is what many students are bothered. How come all of a sudden you know this? I can multiply, but then why do I have to sum? Okay, you can understand. I want to multiply x and y, then x1, y1, x2, y2, x and yn. I get a vector, whereas I get a scalar now. Why was it done? Because I got the length squared of the vector using this formula. Not only that, if you believe in this, I should also get the angle between them using this formula. You follow that? I hope to prove that. So in Rn, if you give me two vectors x and y non-zero, both non-zero, okay, the angle between x and y, okay, I'm going to define this x dot y by norm x and norm y. This is cos of that angle. We want to define. This is again motivated by the earlier one. Do all of you understand? Right. See, this is not the usual algebra lecture. Okay. Right. Now, if you are alert, you know, so you will ask something. Look at the two vectors, cos of something. Remember, the angle must be a real number. Right? Therefore, cos of that angle. So, you know, cos x lies always between -1 and +1. Yes? Do you remember? Cos takes values between -1 and +1. Alright. So cos of that has to be, if you want to define x dot y by norm x norm y, this fellow should lie in the interval -1 to +1. Right? That means mod of this fellow x dot y by norm x into norm y should be less than or equal to 1. That is, mod of x dot y should be less than or equal to norm x into norm y. Okay, is this true? See, we are discovering mathematics, right? Okay, this is what is known as Cauchy-Schwarz inequality. Okay, so before going any further, I request you to watch the video on dot product on Rn. Okay, so in R2, okay, given two vectors, let us say xy and uv, okay, these are vectors in R2, and assume they are non-zero, okay, we define the inner product xy dot uv as we did earlier, xu plus yv. Right? Okay. Now let us, we already showed how this gives rise to the angle between these two non-zero vectors. But there is also something very interesting. So okay, I just want to talk about it. So let us again look at, okay, this is the vector, okay, xy, and this is the vector uv, right? So when I want to go from here to here, okay, let us look at this vector. Okay, this vector is, as you know, uv minus xy, that is u minus x, v minus y. This is this vector, because you have the parallelogram law of identity, the addition, right? Parallelogram law for vector addition. So this plus this vector is this. Am I making myself clear? Right. Now there are three. Okay, now this is what? This is a triangle. Okay, the way I have drawn. Of course, I am assuming uv is not a proportional to or scalar multiple of xy. Therefore, okay, I can form a triangle. Okay, all those things are understood. Now suppose this is the angle theta. Right. Now I can apply a law of cosines. Right. Call this length as a, and call this length as b, and call this length as c. Then what the cosine law says? C is not found. That c squared is a squared plus b squared minus 2ab cos theta, where theta is the angle between the sides a and b. Right. Now let's do that. What does that mean? Yeah, this is u minus x, and what is the length of this vector? This is u minus x whole squared plus b minus y whole squared equal to a squared. A stands for the length of the vector x squared, therefore it is x squared plus y squared plus u squared plus b squared minus 2 times length of the vector. So let me simply write a and b, where a is x squared plus y squared to the power half, and b is u squared plus y b squared to the power half, right? Length of this vector into cos theta. But this side is going to be u squared plus x squared minus 2ax 2ux plus v squared plus y squared minus 3by, right? So you can see x squared plus y squared common here, sorry, x squared, and this is u squared common, and this is y squared goes, y squared goes. Therefore what do I get? So I get 2 times xa, what is xu plus yv equal to ab times cos theta. But what is a? This is the length of the vector x comma y into length of the vector u comma v into the angle between them cos theta, right? This is twice again, sorry, so to cancel. Therefore cos theta is xu plus yv by length of this vector xy and length of the vector vuv, and this is dot product of xy dot product with uv by length of this vector xy into length of the vector uv. You see that? So we again, okay, we did using complex analysis. This time we used, yeah, I'm in tablet form only. Okay, this time we use law of cosines to arrive at the formula for inner product. You understand? Therefore, the inner product of xy dot uv equal to xu, that is multiply these two and then multiply these two and then add. Okay, this is important. Why? Because if I take uv equal to xy, then I get the length squared of the vector xy, and when I take their distinct, then I get the angle between them. Do you follow that? Yeah, right. Okay, so that is why the dot product is very important. So I had motivated in two different ways. Watch the video twice and follow this by dot product on Rn. Okay, you will see your geometric ideas and confidence level of inner product space will be much deeper and higher. Okay, and whatever I said is some kind of, this is the way. See, because what I'm trying to tell you is possibly what took perhaps a few decades or 100 years to arrive at all these definitions very rigorously. Okay, I tried to some kind of, from my limited way, I tried to see how our forefathers, great mathematician, might have thought about these things and arrived at it. It's some kind of a glimpse. Okay, I'm not a good at history, so I'm not sure that's the way they arrived at, but this, I'm sure this will make you think. Okay, before you, the second lecture on IPS, inner product space, is released, please watch dot product and Rn. Okay, I hope you'll do it. Thank you.